Assalamu alaikum, guys, and good evening. So, we are going to continue from where we ended up last time. Just wanted to give you a quick review that in all the mathematical models that we use to understand the enzyme kinetic mechanism, we have certain stages, as I discussed with you last time, and it involves certain assumptions before we conclude towards the algebra or the derivation. So the assumptions that we have made in the Michaelis-Menten kinetics were the first step, which is the formation of enzyme substrate complex, is fast and is always at equilibrium. So we can say that the K1 and K minus 1 are far greater than the K2. K2 was the rate constant for the formation of the product, if you remember. The second assumption is the change of the enzyme substrate concentration with reference to the time is approximately is at zero, which states that it is at steady state, it is at equilibrium. So the rate of the formation of the ES, or we can call it the rate of the breakdown of the ES, are approximately at equilibrium. The third assumption was that there is a single reaction or dissociation step, which is in fact conversion of enzyme substrate complex to enzyme end product. And for that step, the constant is K2, which is being referred to Kcat as well. The total substrate concentration is the sum of the free substrate and the substrate that is bound with the enzyme. And this is roughly equivalent to the total substrate concentration. So we understand that the whole substrate molecule we have provided are attached with the enzyme via the active sites. The last assumption, we said that when the reaction is just started or we just mix the enzyme with the reactant, at this stage, there is no back reaction of product to ENS. That means at this stage, the product is approximately zero. This assumption will allow us to ignore K2 because we are considering the initial rate at this stage. So we measure initial velocities, and by considering that at initial velocities, the concentration of the product is approximately zero. So keep these five assumptions in your mind. And now look at this graph. Now this graph is actually reflecting those assumptions that we have done. We have concentration on one axis and we have time on the other axis. For the concentration, we have the concentration of the enzyme, which is ET, the total concentration of the enzyme, and we have the concentration of the substrate. And here on the x-axis, we have the time. And this is the equation that we have been discussing since last class, that enzyme substrate combine to form enzyme substrate complex. This is a reversible reaction, so it can dissociate back to enzyme and substrate. Their constants are K1 and K minus 1. While in other case, the enzyme substrate complex can further go to dissociate between enzyme and product, and the dissociation constant for that is the K2. So the time dependence of everything is the key in Michaelis-Menten kinetics. So if you see this graph, I'll explain each of the lines one by one. Let's start from the substrate. At time zero, you can see we have the highest concentration of the substrate. And as the time progresses, the concentration of the substrate is going down, going down, going down till it reaches this point. In contrast to the substrate, if we talk about the product, as I said, one of our assumption was that at initial velocity, the product is zero. But as the time progresses, the amount of the product increases and it goes on directly proportional with the time. So we can say that pretty much the substrate and the product, they are going reciprocal when we compare that with the time. In case if we talk about the enzyme concentration, the total enzyme concentration, obviously it will be at maximum at the time zero. But as time progresses, you see that there is a decrease in the enzyme concentration. Why? Because some of the enzyme will be bound with the substrate to form the enzyme substrate complex, and overall the enzyme concentration is decreasing while the enzyme substrate concentration is increasing, because at this point the reaction has just started. Once the time goes on, the enzyme will bound with the substrate, and as a result of this brown line indicating the increase in the concentration of the enzyme substrate complex. And at this point you can see the line becomes straight. Why? That is showing the saturation point where all the active sites on the enzymes have been occupied by the substrate, and with the passage of time there is no change going on in the concentration of the enzyme substrate complex. Similarly, the total enzyme was higher at this point, but after some time when it bound with the substrate, the net enzyme remained, it's pretty much constant, because now there is no change in the concentration going on. The total enzyme concentration is actually, as I mentioned earlier, is the sum of the enzyme plus the enzyme substrate complex. And we know that initial velocity is determined by the rate of the change of the enzyme substrate complex divided by the change in the time, which is approximately zero, because we assume that it is at equilibrium. So all the assumptions that we have done in the last slide are being shown graphically here. So if you are all clear about that, now we move towards the algebra or the mathematical derivation. So this is the key equation that we are considering in Michaelis-Menten. Now what we do is, like, we know that the change of the enzyme substrate with reference to time is actually equivalent to enzyme concentration multiplied by the substrate concentration minus the reverse reaction, which is K minus 1. In the reverse reaction is the dissociation of enzyme substrate complex, and then minus K2, which is the last step of formation of enzyme and product. So this velocity here is being defined as the combination of these three. As you can see here, this K1 reflects to the formation of ES, this K minus 1 reflects the reverse reaction, and this K2 reflects this reaction. And we have made the assumption that all of that is equal to zero because it's a steady state assumption. So we have already discussed about that. Now we solve the ES, and this enzyme substrate complex concentration is actually equivalent to the concentration of the enzyme into the concentration of the substrate. We just taken out this ES and rewrite the equation to get this ES K1 divided by K minus 1 plus K. It's just a rearrangement. We have rearranged this equation and we have separated this enzyme substrate concentration as a separate, and we rearrange the equation. Now define Km. You have been told what the Km is. Km was the concentration of the substrate at which half of the velocity or half of the Vmax is achieved, if you remember. So this Km is actually the combination of all of these constants according to Michaelis-Menten. So Km is equals to the sum of K1 plus K2, sorry, K minus 1 plus K2 divided by K1. So if this is whole equivalent to Km, we substituted Km in place of this formula here to get this equation. We again rearrange the equation. We take the Km out and it becomes E into S divided by enzyme substrate complex. Now going further, we know that this we have just done this Km is equal to this. Now we substitute the enzyme concentration, which is according to our assumption is equivalent to the total enzyme concentration minus the enzyme substrate complex, because this is what we have the total enzyme, and this is what we have the enzyme bound with the substrate, and that is what we have the enzyme left. So that will give you the total enzyme. So we substitute this in place of this E and we get this equation. We multiply both sides by enzyme substrate complex. To solve the ES, we got this equation. ES is equals to E naught into S divided by Km plus S. Now we multiply both sides by K2, and this get the velocity of the reaction. So when we multiply K2 on this side and this side, that is being transformed into velocity, which is the change of the product divided by change of the time, and we got this equation. And we also remember that this K2 into E naught is actually equivalent to V max. So that means in place of this we can introduce Vmax. And as a result of this, we got this Michaelis-Menten equation. So this V is the velocity, which is equivalent to maximum velocity multiplied by the substrate concentration divided by the Km plus substrate concentration. This particular equation is referred to as Michaelis-Menten equation. And you can see from this formula, this is mainly used to calculate the initial velocity. But as you know, the mathematical rule that if you have got, let's say, 4 variables in an equation, and you have 3 variables known, then you can calculate the fourth one. So that means this equation can be used for the determination of initial velocity, it can be used for the determination of Vmax, and it can be used for the determination of the Km as well. So this is what we call the Michaelis-Menten equation, which is the most adapted kinetic model to explain the kinetic model of enzyme activity. So this Michaelis-Menten equation is further being derived when we know that the half of the Vmax is achieved. Half of the Vmax, we know that substrate concentration is equals to Km. So at this stage, this Km can be replaced by S, and as a result of this, we solve this equation, and this gives us Vmax divided by 2. So you can see that this initial velocity is the half of the Vmax. This is saying that when Km is equal to the substrate concentration, the reaction runs at half maximum velocity. And theoretically, I already have told you that Km is that substrate concentration at which half of the maximum velocity is achieved. And this mathematical expression is going to show that when the S is equal to Km, we substitute the S in place of Km, and we got this equation. Now the velocity is half of the Vmax at that concentration when S is equals to Km. Now graphically, we can explain the Michaelis-Menten equation simply by this. And this graph has already been studied earlier on, if you remember. So at time 0, we have, there is 0 velocity. But as you increase the substrate concentration, the initial velocity increases. And it reaches this point where it is half of the Vmax, and this particular concentration of the substrate is called Km. If you further increase the substrate concentration, velocity will further increase till it reaches this point where the graph would become straight. That means no more increase in the velocity takes place, and that is what we call the Vmax. So Km is the substrate concentration required to reach half of the maximum velocity. Now let's talk about further that what is the significance of the Km. There is a lot of significance of the Km. That's why we are talking about much. And as you have just done in this slide, you know that, where is that? Let me show you. Yeah, this one. You know that the Km is actually the ratio of the K minus 1 plus K2 divided by K1. So it's actually the overall reaction coefficient for the reaction. So it must have significance. And what is the significance? We're going to talk about right now here. So as I said that Km is equal to this one, or you can say Km is equals to enzyme into substrate divided by enzyme substrate complex. So actually Km is being defined as the dissociation constant of enzyme substrate complex. A dissociation constant is a Kd, which is the reciprocal of the equilibrium constant, which is Ka. So Km is actually a measure of a substrate affinity for the enzyme, but it is the reciprocal of the affinity. Let me explain that a little bit more. Actually, Km is a constant value. Every enzyme catalyzed reaction where we explain the enzyme kinetics by a Michaelis-Menten model, that particular reaction would have a Km value because it's a constant. And by knowing the Km of a reaction, we get an idea about the measurement of the affinity of the substrate towards enzyme. Why it is important? It is important because the more the affinity of the substrate for the enzyme, the more will be the product formation and more will be the velocity of the reaction. So that's why Km is of the significance. So if K1, K minus 1 is greater than K2 as we did the assumption, then Km is equals to Kd. That means it is equivalent to the dissociation constant. Which dissociation constant I'm talking about? This one, right? So the Km is the substrate concentration which is required, as I already mentioned, to reach half of the maximum velocity. A small Km means substrate bind tightly to the enzyme. And as a result of the substrate bind tightly to the enzyme, the overall activity of the enzyme catalyzed reaction will be slowed down. Why? Because when the substrate bound with the enzyme tightly, it's not going to dissociate into enzyme and product. So you understand, if we have a small Km value of a particular reaction, that shows that substrate will bind tightly to the enzyme and saturates the enzyme. And as a result of this, the enzyme process will be slowed down. Just reverse the situation. A large Km means the substrate bind loosely to the enzyme. And that means it will be less saturated because as substrate bind, it quickly transformed into enzyme and product and it's available for more substrate to bind. And that's how the reaction is increased. So the microscopic meaning of the Km depends on the details of the mechanism. So now you can understand that by knowing the Km of a reaction, you can have an idea about the mechanism of the reaction. You can find out about the initial velocity. You can find out about the affinity of the binding of the substrate with the enzyme and rest of the other factors. So that's why knowing the Km of the reaction is of the significance. Similarly, the Kcat or the K2 also has got significance because we know that the max when we have the maximum velocity at this point we have the total enzyme available, or you can say it's directly proportional to the total enzyme. And if we incorporate a constant, that will be Kcat. Why Kcat? Because total enzyme means the dissociated enzyme once the substrate has been transformed into product. So in case the Kcat, for the simple possible mechanism where enzyme substrate is the only intermediate and dissociation is fast, in that case the Kcat is equal to K2. That means as soon as the enzyme substrate is formed, it's quickly dissociated into product. So the first order rate constant for the catalytic step is that Kcat is equals to K2. If dissociation is slow, then the dissociation rate constant is also contributing towards the Kcat. If one catalytic step is slower than the other, and then the decision step is then slower, the rate constant for that step is approximately equivalent to Kcat. So it depends that how quickly the enzyme substrate combine and how quickly they're going to dissociate. So Kcat is actually being defined as the turnover number, which I already have explained yesterday. It is the turnover number and it indicates the rate at which the enzyme turns over, means convert the substrate into product. In other words, how many substrate molecules one catalytic site convert to the substrate per second. That is what the turnover is. And Kcat is actually the turnover. If there are multiple catalytic steps, like for some reactions you have more than one steps, then each of these rate constant contribute to the Kcat. Like if we consider a reaction which is a single step, then in this case the Kcat is equal to the dissociation constant. But if you have got a reaction where you've got multiple steps, then each step would have its own rate constant which contributes towards the Kcat. So the microscopic meaning of the Kcat depends on the details of the mechanism, just like the Km. The significance of Kcat versus Km, the ratio. So we understood that if we know the Km value of a reaction, we have certain applications. If we know the Kcat value of a enzyme catalyzed reaction, there are benefits of that. And if we know both of them, we can find out its ratio, and that ratio has got also the significance. And what is the significance? The ratio of the Kcat versus Km is showing the catalytic efficiency. And what is catalytic efficiency? Again, the efficiency of the enzyme to catalyze the reaction. This catalytic efficiency is used to rank enzyme. What is the meaning of that? A big Kcat Km means the enzyme binds tightly to the substrate, which I already mentioned, that means small km, with a fast reaction of the ES complex. While in other case, a small kcat Km means that enzyme binds loosely to the substrate. That means a large Km. So kcat upon Km is also as an apparent second order rate constant, where the velocity is equals to kcat upon Km multiplied by the enzyme concentration into the substrate concentration. So in this case, kcat upon Km can also be used to estimate the reaction velocity from the total enzyme concentration. Kcat Km is a specificity constant. It is used to distinguish and describe various substrate binding as well. So we have significance of Km, we have significance of Kcat, we have significance of the ratio of the Kcat upon Km. Now, the next thing is the data analysis. What does that data analysis mean? We know that in certain cases, there are enzymes where to do the data analysis on the Michaelis-Menten graph is getting difficult. Let me explain you what actually I mean. If I go back to the graph which I showed with you, just to give you an idea what actually I wanted to explain. This one. Now, this graph is not a straight line graph. It's a curve graph, you can see. On a curve graph, it is very difficult to calculate the slope. I'm not sure that whether you guys have done that in the mathematics, but there are two types of the graph. There's a straight line graph, which is normally starting from there and it goes like this. And this is what we call the curve graph. It could be hyperbolic or it could be parabolic. Now, mathematically, if we have to apply the straight line equation or we have to calculate the slope, mathematically, it's very difficult to calculate the slope on a curve graph as compared to a straight line graph. Now, why we are interested in the slope? Because as you can see here, we have determined the half Vmax, and this is what we call the slope calculation. So in this case, it's pretty much hard mathematically to apply the straight line equation to determine different variables with the help of the curve graph. What actually we wanted to make it more simplified in terms of the graph, so where we can have a better understanding of how we can calculate the slope. Now, in order to resolve this issue, there are a couple of other mathematical models deduced. And one of the model that we're going to discuss here is called Line-Weaver-Burke plot. Now, these are again, two scientists who actually proposed this model, and they have actually rearranged the Michaelis-Menten graph in a different way to make it a linear plot. So in this case, it would be useful to have a linear plot for the straight line equation, what we call the MM equation. As I said that straight line equations are difficult to, or the slope is difficult to be done on a curve graph. So what they did, they transformed the Michaelis-Menten graph into a straight line plot or a linear plot. And that linear plot is being called as Line-Weaver-Burke plot. And what they have done actually, they have taken the reciprocal of the both sides and rearranged. If you look at the Michaelis-Menten graph, they haven't changed anything. What has been taken on the x-axis and what has been taken on the y-axis, they have just taken their reciprocals. What does that mean? If you go back again to the graph here, on the y-axis we have velocity and on the x-axis we have substrate. What they have done, instead of substrate, they have taken 1 upon substrate. That means reciprocal. And instead of velocity, they have taken their reciprocal 1 upon v. So just taking the reciprocals of these two, they have converted a curved graph into a straight line graph. Now, we'll do some mathematics for this. If this is the Michaelis-Menten equation we discussed, we take the reciprocal. You can see that what we have, this v, we have taken 1 upon v. And as a result of this reciprocal, the graph is now being plotted between 1 upon v versus 1 upon s instead of v versus s. So on the y-axis, instead of the v, we are taking 1 upon v. And on the x-axis, instead of s, we are taking 1 upon s. Now, what is the benefit of doing this? I'll show you on the graph it will be more easier to understand from the graph. Now look at this graph. Here we have on the x-axis 1 upon s, and on the y-axis we have 1 upon v. And I'm sure that you guys know that this is what we call the positive axis. And if I go in this direction, it's called negative axis. And if I go in this direction, it's called negative axis. We all know about that. So we have taken it up to the negative axis because we have a straight line. This is what I'm calling about Line-Weaver-Berg plot. Now, when we plot the graph between 1 upon v versus 1 upon s, we got a straight line instead of the curve. Now, there are a couple of advantages of this straight line. What are these advantages? If you see this line is going to intercept the y-axis at this point. This point of intersection where this line touches the y-axis is mathematically called 1 over Vmax. 1 over Vmax means half Vmax. So in contrast to this graph, if you go there again, the calculation of the Vmax, half of the Vmax was difficult because in this case you have to apply the straight line equation and then calculate the slope and then do the things. But in this case, it's quite simple. Whatever this line refers to the value on this side can give you the half of the Vmax. Similarly, the slope calculation of this graph will give you the Km upon Vmax value. You can calculate out the substrate concentration at which the Km is achieved. And also the x-intercept of, if you go back on the negative side, this line is going to touch the x-axis. And this x-axis is going to give you 1 upon Km. That means half of the Km. So that in this case of the Line-Weaver-Berg plot, the y-intercept is giving you 1 upon Vmax, and the x-intercept is giving you 1 upon Km, and the slope is giving you Km upon Vmax. Now, the point is that all of these things can be calculated from the Michaelis-Menten, but it was much difficult. In this case, it's a straight line graph. So what Line-Weaver have done, they have just reciprocate the values of the Michaelis-Menten graph that they have taken on the x and y axis, and by reciprocating, they got a straight line, and that straight line will help and facilitate them to do these calculations quite simply, quite easily. So this is all about the Line-Weaver-Berg plot. Let me tell you that there is one more advantage of this Line-Weaver-Berg plot. And this advantage can be in terms of different types of inhibitions. If you remember, last time in the first lecture, we discussed about competitive and non-competitive and uncompetitive inhibitions. And they do have, differences. Just to recall, competitive inhibition was where an inhibitor is competing with a substrate for its binding to the enzyme. The non-competitive was where binding of the inhibitor is different from the site where the substrate is binding. So you can recall that. So this Line-Weaver-Berg plot is also a very, very smart tool to graphically show the difference of different inhibitors in terms of their kinetics. So let's talk about this table. We have three types of inhibition. We have competitive, uncompetitive, and mixed, which is being called as non-competitive. And I'm sure that competitive and uncompetitive is quite simple. So in this case of the competitive inhibition, the effect of inhibitor increases with the Km. Why in uncompetitive, it decreases with the Km. And I think the reason is quite simple, because in case of the competitive, the inhibitor is competing with the substrate. So if you increase the concentration of the substrate, automatically you can overcome the effect of the inhibitor. In case of the uncompetitive, increasing the substrate concentration is not going to affect because the inhibitor is binding to a different site. So in other words, we can say that in competitive inhibition, if we increase the Km, we can reduce the effect of inhibitor. In case of uncompetitive, if we decrease the Km, we can reduce the effect of the inhibitor. In case of the mixed or the non-competitive inhibition, it's a kind of inhibition where actually it's not competing, but there is a chance that a substrate can bind to that place where the substrate was supposed to bind. Now, in this case, decreasing the Vmax may increase or decrease the Km, and that's how you can reduce the effect of the inhibitors. I am not sure that whether we have the graph here. If we don't have that graph, I'll share the graph later on, because there is a graph I wanted to share, which is a Lineweaver-Burk plot to explain these three inhibitions. And I wanted to let you know that how these three different type of the inhibitions can be easily understood by looking at the Lineweaver-Burk plot, while it's quite difficult to explain them with the help of the Michaelis-Menten graph. But it's not here at this stage. Maybe it's down the slide somewhere. If it's not there, I'll share it later on. So this is the explanation of these inhibitions a little bit in a more detailed way. In competitive inhibition, it's quite simple. Enzyme bind with the substrate. Enzyme can bind with the inhibitor. So inhibitor is competing with the substrate, right? If the inhibitor binds, it forms enzyme inhibitor complex, results in no reaction. But if substrate binds, it's form enzyme substrate complex and then followed by product and enzyme. So I think competitive inhibition is quite simple. So in case of the competitive inhibition, we say that inhibitor dissociation constant will be K1, because if enzyme bound with the inhibitor, the dissociation constant for this will be called as K1. Now the total enzyme is actually the enzyme minus the enzyme substrate complex minus the enzyme inhibitor complex, because there is some possibility that inhibitor bind with enzyme as well. So in this case, one can say that this coefficient, dissociation coefficient, will be equivalent to the total concentration of the inhibitor divided by the inhibitor dissociation constant. And if we substitute that value in the equation of the Lineweaver-Burk plot, we got 1 over V is equals to alpha Km substrate divided by Vmax into S, which is rearranged into alpha Km divided by Vmax S plus 1 upon Vmax. And now that was the graph I was actually talking about. Now this is the Michaelis-Menten graph, and this Michaelis-Menten graph is in showing you what the competitive inhibition looks like. This green line is the ordinary line where there is no inhibitor, and you can see this is the Vmax, half of the Vmax, and this is the Vmax. In place of the inhibitor with a slight concentration of inhibitor, what actually happened? If you compare this green line with the blue line, what has been changed? You can see that the final velocity or the Vmax has been changed. If you have more inhibitor concentration, more decrease in the final velocity. So what we concluded out? We concluded out that as a result of the competitive inhibition, because the inhibitor is competing with the substrate for its binding onto the enzyme, the overall maximum velocity is decreasing. So more the competitive inhibition, less will be the Vmax. I think it's pretty much clear at this stage. Okay. Now this is the Lineweaver representation of the same condition. This is the competitive inhibition. Now in the competitive inhibition, this green line indicates no inhibitor, this one indicates inhibitor, and this one indicates more inhibitors. And you can see that all of them are converging at one point. What it shows that the competitive inhibition will not affect the half of the Vmax, but it does affect the Km values. You can see in absence of that, this was the Km value. In presence of the inhibitor alpha 2, that means little amount, that was the Km. And in case of this, it's actually increasing because it's a negative axis. So this is the least value, the Km is increased, and the Km is further increased here. So what we have seen here, that with this Lineweaver plot is much easier as compared to this to understand, because in this case, if we have to calculate the Km, we have to draw the slope to understand Km, then 2 Km, then 3 Km, and then it was difficult. But in this case, it's quite simple. The intercept on the x-axis are giving you the Km value. So this is the least Km value, which is in the absence of inhibitor. When you have got alpha 2, the Km value is increased. Then you have got more inhibitor, Km value is further increased, while it's not affecting half of the Vmax, as you can see here. The half of the Vmax is not affected by competitive inhibition. So now you understand that this Line-Weaver-Berg plot is going to explain you about these parameters if an inhibition takes place, that how it affects the mechanism and the kinetics. This is example of the competitive inhibition. I'm not going in the detail for that, but product inhibition like ADP, AMP can competitively inhibit enzyme that hydrolyze ATP. So this is what the example of a competitive inhibition. This is another example of competitive inhibitors which inhibits and compete with the substrate. Now the second one is the uncompetitive inhibition. The uncompetitive one, I think it's pretty simple. Enzyme bound with the substrate to form ES. This ES can be converted to product and enzyme, or this ES can bind with the inhibitor to form enzyme substrate inhibitor complex, and then there is no reaction. So here it's very simple that inhibitor is not competing for the binding. Its binding is separate from the binding of the substrate, and that's what is uncompetitive inhibition is. So in this case of the uncompetitive inhibition, the enzyme substrate complex multiplied by inhibitor concentration divided by enzyme substrate inhibitor complex will be equivalent to K1, which is the inhibitor decision constant for this kind of the reaction. And the total enzyme concentration will be enzyme minus enzyme substrate complex minus enzyme substrate intermediate complex. And we incorporate these values in the Line-Weaver-Berg plot to get this equation. Now, if we plot the graph, this is the graph, the Line-Weaver-Berg plot of an uncompetitive inhibition. Now, compare that with the competitive. What differences you can see? You can see here that in case of the uncompetitive inhibition, it's not only changing the Km, but it's also changing half of the Vmax. So I think this is pretty much clear here that in case of the uncompetitive inhibition, if we draw the Line-Weaver-Berg plot, it's not only changing the Km, but it's also affecting half of the Vmax. If I go further in detail, I can say that in presence of the uncompetitive inhibitors, the Km value is decreasing, while in case of the competitive, the Km value was increasing. And also the half of the Vmax is increasing in presence of the uncompetitive inhibitors. So I think you can see that why the Line-Weaver-Berg plot is more easier in order to see how different inhibitors are working. The third and the last is the mixed, what we call the competitive and uncompetitive inhibition. Now what's going on in this case? We have enzyme plus substrate to form complex, and then product and enzyme, which is the normal route. This enzyme can bind with the inhibitor. That means it's kind of a competition to form complex. Or this inhibitor can bind to the enzyme substrate complex as well. So it's actually the combination of both competitive and uncompetitive inhibition, and that's what we call the mixed inhibition. If we plot that in terms of the Line-Weaver-Berg plot, this is the graph. What you can see the differences here. The difference is that in presence of the inhibitor, this is the graph, the green one. In presence of, in absence of the inhibitor, this green one. Then when you have inhibitor, the Km is increased. When you have more inhibitor, Km is further increased. That was the case of competitive, if you remember. While the Vmax is also changing, which was the case of uncompetitive. So now this graph is showing you that both half of the Vmax and the Km are changing because it's the combination of competitive and uncompetitive. So we have Km increase as a result of this, which was the characteristic of competitive inhibition. And we have Vmax, half of the Vmax increase, which is the characteristic of uncompetitive inhibition. So we have both combined here, and that's how the Line-Weaver-Berg plot is going to explain how it affects the enzyme kinetics. So I'm sure that from this graph, I think it's pretty simple to understand, like if these graphs are being plotted in front of you, you can identify that this particular graph is showing competitive inhibition or uncompetitive inhibition or mixed inhibition. Because if you remember the parameters that what's going to be affected, you can differentiate the Lineweaver-Burke plot and can easily differentiate what type of inhibition we are talking about. This is another effect of inhibitor on the Michaelis-Menten reaction. I want to show you with a graph. It's more easier. Uh, Sorry, just hold on. No, the last two slides are not the part of the discussion, so I'm not going to discuss this. So we'll end up here that this is the effect of inhibition on the Michaelis-Menten reaction. So what I want to say that whatever we have explained about the competitive, uncompetitive, and mixed, it can be explained on the Michaelis-Menten reaction as well. But graphically explaining that on the Michaelis-Menten graph is much difficult. That's why we have used the Lineweaver-Burke plot, which is the reciprocal of that, which gives us a better understanding of these competitive, non-competitive, and mixed competitive or mixed inhibition strategies. So we are going to stop here, and I have already shared the presentation with you guys. So if you have got any question at this stage, you can raise your hand and ask the question. Okay, so if there are no questions, we're gonna stop the class here, and then inshallah we'll share the recording once it is available. Thank you very much, and Khuda Hafiz.